Dear students, so welcome to another video lecture. We will continue our discussion about the LTE, 4G LTE. So, this class, in this video lecture, we will start discussing about the LTE channel structure. Okay. So, in the last class, we started the concepts of LTE, and we stopped at this point where we were discussing about the LTE protocol stack. So now we will discuss about the LTE channel structure. So there are three types of channels in LTE, and these channels they provide services to the layers above. Okay, so if you look into the different protocol layers of the LTE, so if you have the different layers, so this is the PHY layer, then this is the MAC layer, and so on. So in between the different layers, there are these logical channels, okay, which provides services to the layers above. Okay, so the logical channels, they provide services from the MAC layer to the RLC layer, okay, and provide a logical connection for control and traffic. Okay, then there are transport channels which provide PHY layer services to the MAC layer, and they define modulation, coding, and antenna configurations. And then there are physical channels that define the time and frequency resources used to carry information to the upper layers. Okay. So there are three different types of channels: logical channels, transport channels, and physical channels. And then among these three main categories, there are subcategories based on whether it's a broadcast or a multicast or a paging or a shared channel. Okay, so the radio interface architecture and the SAPs are shown here. So you have the physical layer, then the MAC, RLC, PDCP, etc. And then in between the different layers, these channels are there to establish connection between these different layers. Okay, so you have the logical channels, transport channels, etc. Okay, so this picture gives you a more detailed overview of the channel. So this shows you the mapping of the logical, transport, and the physical channels. Okay, so these are the logical channels. Okay, and then between the MAC layer and the physical layer, you have the transport channels. Okay, so these are the transport channels. All of these acronyms has a complete expanded name. The CH stands for channel. So between the physical layer and the MAC layer, you have these transport channels, and then there are the physical channels which reside beneath the physical layer, and these are all the physical channels. Okay, and then you have this mapping between the different channels based on what actually these channels are communicating. Okay, so these are abstract concepts. So these are it doesn't mean that there is a don't confuse the term channel here from the actual concept of channel that you have learned so far. So in wireless communication and digital communication, what you mean by channel is the one that stays between the transmitter and the receiver, let's say. So between the transmitter and receiver, you have a channel. But this channel, these are logical entities. Okay, these are abstract entities. Okay, and they actually mean, I mean, in the context of LTE, the channels mean the connection between the different layers of the LTE protocol stack. Okay, and each of them has different functionalities. Okay, so let's look into those functions. So there are different physical channels. Among the physical channels, again, there are physical downlink channels and physical uplink channels. So the physical downlink channels are these. So physical downlink shared channel, which carries the downlink shared channel and the physical channel. The downlink shared channel contains actual user data. Okay. Then the physical downlink control channel. So this informs the UE about the resource allocation of PCH and DLSCH, and also the hybrid ARQ information related to DLSCH. Okay. This carries the uplink scheduling grant also. Then you have the physical HRQ indicator channel. So this carries the AX and NAX in response to uplink transmissions. So as you can see that these different channels have different specific functions. Okay. Physical control format indicator channel, physical broadcast channel. So there are different channels in the LTE architecture. Then the physical uplink channels, among them are the physical uplink shared channel, physical uplink control channel, physical random access channel, etc. And each of them has different functionalities. Okay, so I'm not going through much details of these channels. So there are all these functions written here briefly. These are basically, you know, if you are a practicing engineer, let's say, you want to design an LTE system, then all this information will be available in the standards manual. Okay, so basically there is nothing to, um, right now there is nothing to explain much about these. So they have specific functions related to different different tasks in the communication procedure. Okay, so for example, carrying the AX and NAX, so carrying the random access preamble, etc. Okay, so each of them are carrying or performing a specific task, all these channels, and they are imaginary abstractions. Okay, they doesn't exist in the actual, how should I say, in the actual um, communication of bits, but when you are trying to define a standard and trying to design a system, then these things are there to define specific functions. Okay, so these are a way of abstracting the actual communication. So just like, you divide the different protocols into different layers, and then within those layers, in between those layers, while you are exchanging some information between those layers, you are doing those through these channels. Okay, so then we have the logical channels. Okay, so under them there are many categories. Okay, so for example, the broadcast control channel, the paging control channel, the common control channel, the dedicated control channel, and so on. Okay, so again, I'm not going through the detailed explanations of these, but these are the high level functions of these different channels. Okay, then you have the downlink transport channels. So again, they have different categories under them: the broadcast channel, the downlink shared channel, the paging channel, the multicast channel, etc. And then you have the uplink transport channels. So here you have the uplink shared channel and the random access channels. Okay, again, each of them has a specific function or a specific sets uh, of functions. Okay, so let's move on with the LTE radio access network. So LTE uses MIMO and OFDM. So you have come across these information before. So let's look into the details of that. So usually the OFDM part is used on the downlink. Okay, And for the uplink, there is this single carrier OFDM which provides better energy and cost efficiency for battery operated mobiles. So those of you who have gone through my digital communication class, they have come across OFDM, or depending on when you are actually listening to this video lecture, whether you have gone through the OFDM part in your digital communication or not, um, you will come to know that OFDM has a disadvantage associated with the peak to average power ratio, okay, which is called PAPR. Okay, in OFDM you have multiple subcarriers, okay, that are modulated individually and then transmitted together. Okay, so because of that, because of many subcarriers that are added together, the power level of the OFDM signals are high. Okay, and that causes certain problems because the amplifier circuits that are used in the transmitters and the receivers, they may go beyond their linear region of operation. Okay, so because of that, there is this PAPR, or peak to average power ratio, issues in OFDM, and that's why in LTE the single carrier OFDM is used for the uplink, because for the uplink it's basically between your mobile phone and the E node B. Okay, so for the uplink, your mobile phone is operated on a battery. Okay, and here you cannot have this this high power consumption because of PAPR, and that is why the mobile phone transmitters, they operate on single carrier OFDM for LTE, and the E node Bs, they operate on OFDMA. Okay, so usually the LTE uses subcarriers that are 15 kilohertz apart, and again this is a aspect of OFDM which those of you who have not taken my digital communication class, there is a fraction of the class which are not part of my digital communication class. They may not know, or they may know, I don't know, that OFDM uses fast Fourier transform. Okay, and the maximum FFT size for this LTE based OFDM is 2048. Okay, so that means you can have 2048 number of subcarriers at the maximum. Okay, so 15 kilohertz is the bandwidth of each of these subcarrier. Okay, so the basic time unit TS is 1 over 15,000 times 2048. Okay, so 15 kilohertz is 15,000 times the number of subcarriers at max. So these two numbers multiplied, and then you take the reciprocal of that to get the basic time unit of LTE, which is these many seconds. Okay, now the downlink and the uplink, they are organized into radio frames, and the duration of the radio frames are usually 10 milliseconds, which corresponds to these many TSs. So where TS is the basic time unit. Okay, so LTE uses again both TDD and FDD. So TDD means time division duplexing, and FDD means frequency division duplexing. So both have been widely employed. So in case of your TDD, the uplink and downlink transmit in the same frequency band but in the alternating time slots. Okay, or alternating in the time domain. I will soon show you a picture to emphasize these concepts. And the frequency division duplexing, they use different frequency bands for uplink and downlink. Okay. And again, since you are using OFDM, so there are the cyclic prefixes which are associated with OFDM. So basically, the cyclic prefix, they are used with one OFDM frame to combat the effect of the wireless multipath. Okay, again, those of you have gone through my OFDM lecture, they will know more about this multipath. So I would suggest the EIE students who are taking this wireless communication module and are not enrolled in my digital com, they somehow, if they can watch the OFDM video lectures that I have for digital com, they will be able to appreciate these things better. So the cyclic prefixes for LTE are of two types. Okay, so there is a normal CP which is 144 times the basic time slot, so the total cyclic prefix length in terms of time will be 4.7 microsecond, and in case of very worse wireless environments, like when the multipath effect is very high, you use an extended cyclic prefix which is 512 times the basic time slot, and that would give you a 16.7 microsecond length of a cyclic prefix. So talking about FDD and TDD, so this is what is meant. So in case of FDD, you are using the entire time slot, the radio time slot of 10 milliseconds. So if you go here, the radio frames, they are of duration 10 milliseconds. So in case of your FDD, you are using the entire frame of 10 milliseconds for downlink. So this blue indicates a different frequency, the green indicates another frequency. So let's say at frequency F1 you are using the entire frame for downlink information, and at frequency F2, let's say, you are using the entire frame for uplink information. Okay, so this is frequency division duplex, so for downlink and uplink, so both directions are happening as a part of this duplex, but on different frequencies. For TDD, you are using different parts of this time slot. You are using the same frequency, so the frequency remains the same, but you are using the different parts of this time frame for downlink and uplink. Okay, so you are using this part for downlink and then this part for uplink, etc. And then this S denotes some special subframes. Okay, so we will see what are those later. So let's look into the detailed frame structure. Okay, so the FDD frame structure. Let's look first into the FDD scenario, and then in the FDD also we have different types. So let's look for the FDD frame structure type 1. So here you have three different time units. So the slot, which is T slot, which is 15360 times the basic time unit, and this corresponds to 0.5 milliseconds. Okay, so two consecutive slots comprise a subframe of length 1 milliseconds. Okay, and 20 slots or 10 subframes equal to one radio frame, which is 10 milliseconds. So that is what you already know. So one radio frame is 10 milliseconds, and then these radio frames are divided into 10 subframes, and each subframes have two slots. Okay, so that's how the division occurs. Okay, and then you have the cyclic prefix. So normal CP allows 7 OFDM symbols per slot. Okay, so one slot is 0.5 milliseconds. So if you use a small cyclic prefix, then you can have more OFDM symbols, because the total time slot is fixed. Okay, and then if you use extended CP, only allows you to 6 OFDM symbols. So use of extended CP results in a 1/7 or 14.3% reduction in throughput, but then it provides better compensation for multipath. Okay, so this is what we were just discussing. So this is the frame structure. As you can see, you have 20 slots, 0 to 19. Okay, so this is one complete radio frame of 10 milliseconds. Okay, and then within that radio frame you have one subframe of 2 slots. Okay, so you can have 10 subframes, or in other words you can have 20 slots which are numbered 0 to 19. Okay, now if you zoom into one of these slots, then if you use normal cyclic prefix, okay, then you can have 7 OFDM symbols, okay, 0 to 6. But if you use an extended cyclic prefix, then you can have only 6 OFDM symbols, 0 to 5, because this length is fixed. So depending on your cyclic prefix length, you can have either 7 or 6. Okay, so each OFDM symbol is 66.7 microsecond long. Okay, so now if you are using a higher cyclic prefix, then that corresponds to a small number of symbols. Okay, now there is a TDD frame structure which is the type 2. Okay, so my apologies, I said for FDD you have 2 types, but actually FDD is the type 1 and TDD is the type 2. Okay, so again, in case of TDD frame structure, the radio frame is 10 millisecond again, but here you have some special subframes for switching downlink to uplink. Okay, so if you go back few slides, so here you can see that this is one radio frame of 10 milliseconds. So for the TDD case, and then you are using time division duplexing for downlink and uplink, and then you have these special subframes. So these special subframes are used for switching downlink to uplink. Okay, so within the special subframes you have these parts. So you have the downlink pilot time slot, which ordinarily which is ordinary but shorter downlink subframe of 3 to 12 OFDM symbols. Then the uplink pilot time slot, which is short duration of 1 or 2 OFDM symbols for sounding reference signals or random access preambles. And then there is this guard period. So these are the remaining symbols in the special subframe in between to provide time to switch between the downlink and the uplink. Okay, so this diagram will give you a better understanding. So here this is the TDD frame structure. So you have one radio frame of 10 milliseconds, and then you can divide it into half frames of 5 milliseconds each, and then within the half frames you can have 5 subframes. Okay, so these are the nature of the subframes. Okay, the subframes are again divided into 2 slots. Okay, so one slot corresponds to one subframe, and then these special subframes they contain these 3 different fields. This DWPTS, the guard prefix, the guard period, and the UPPTS. Okay, so so these were the frame structures for both TDD and FDD. So now let's look into some more details. So let's move into the concept of resource block. So basically a resource block, this is a time frequency grid. Okay, and it is used to illustrate the allocation of the physical resources. Okay, so each column, so in the grid, okay, so it will be a grid like this, and then there will be rows and columns. Okay, so each column each of these columns, these will be 6 or 7 OFDM symbols per slot, and each row corresponds to a subcarrier of 15 kilohertz. Okay, so so this is how a resource block looks. Okay, so if you look, let's say in the x direction, okay, so this x direction corresponds to time. Okay, so these are exactly equal to one slot within a radio frame. Okay, so this is the radio frame of 10 milliseconds. Then you have these subframes, and each subframe has two slots. Okay, so each slot within a radio frame corresponds to the x-axis of the resource block. Okay, so you can have 1, 2, 3, 4, 5, 6, 7. So between 6 to 7 OFDM symbols. Each of this time axis. Okay, so if it is an extended cyclic prefix, then you have 6. If it is a normal cyclic prefix, you have 7. And the y-axis actually corresponds to the frequency dimension, and these are all those subcarriers. Okay, so these are the different subcarriers. Okay, and each of them is 15 kilohertz in width. Okay, so therefore each resource element, okay, is one of the small squares. Okay, this is denoted by K and L. So where K represents the number of symbols in the time domain, and L represents the number of subcarriers. Okay, so so between this K equal to 0 to this is the maximum value of K. Okay, and L is between 0 to this. Okay, so basically how many symbols you have for downlink. So this is 6 to 7. Okay, for uplink you are using single carrier OFDM, so that is a different thing. Okay, so for downlink you are using the OFDM symbols, and they are 6 to 7. So depending on that value, this L will be between 0 to 5 or 0 to 6. Okay, so N this number N DL, okay, symbol will be either 6 or 7. So L will be 0 to 5 or 0 to 6, and the subcarriers, okay, so there will be total these many resource blocks. Okay, and within one resource block you will have these many subcarriers. Okay, so N RBSC subcarriers. Okay, so the value of K is basically as many resource blocks times as many subcarriers in one resource block. So this number minus 1. So K will range from 0 to this product minus 1. Okay, so this is the entire grid, okay, of time and frequency that is used in LTE. So this is the entire resource grid. Within this resource grid you have several resource blocks. Each resource block will have a certain number of subcarriers. Okay, and between 6 to 7 symbols. So therefore each resource block will have NSCRB times this 6 or 7. Okay, these many small resource elements. Okay, these small squares. Okay, so each of the small resource elements, they carry some information that actually is meant to be carried over an LTE connection. Okay, So resource block, so there are 12 subcarriers actually. Okay, so this number n RBSC, so this is basically 12. Okay, uh, so and then you have 6 or 7 OFDM symbols. So therefore each resource block will have 72 or 84 resource elements. So these resource elements, these are the small squares here. Okay, so there will be 72 to 84 resource elements. So for the uplink case, you have contiguous frequencies that must be used for the 12 subcarriers. Okay, this is called a physical resource block. For the downlink, the frequencies need not be contiguous, because for downlink you are using single carrier FDMA. So basically, so if you see this this arrangement here, OFDM versus single carrier FDMM. So OFDM is used. OFDM is used for the downlink part. Okay. So in the OFDM, each of these subcarrier has to be contiguous. Okay. So they have to be one after the another. Okay. So this is for downlink. For uplink, you have SCFDM, and you don't need to be having contiguous subcarriers. Okay. So that's what is meant when it is said that that for uplink you have contiguous frequencies for the 12 subcarriers, and for downlink you don't need to be contiguous for the frequencies. Okay, so in release 8, the only supported bandwidths are 1.4 megahertz, 3 megahertz, 5, 10, 15 and 20. Okay, so therefore the number of usable resource blocks allowed in each of these bands is following. So the physical resource blocks, or the number of contiguous frequencies that you can use, for 1.4 megahertz band it is 6, for 3 megahertz band it is 15, for 5 megahertz 25, and so on. So if you see that each of these are 15 kilohertz. Okay, so for the remaining, so if you multiply this resource blocks, okay, with the number of subcarriers that they have, then that won't make these numbers. Okay, that will be less than these numbers. Okay, so the remaining subcarriers are actually reserved for guard subcarriers and cannot be used for any transmissions, either in the uplink or in the downlink case. Okay, so that's what is meant when I say that if you multiply these numbers with the actual bandwidth of each of these resource block, then it won't make 1.4, 3, etc. So there will be some remaining bandwidth, and they are used for this guard bands. Okay. So LTE uses MIMO. So you have this either you have 4x4 or 8x8 for LTE advanced. So in case of this MIMO, so separate resource grids are used per antenna port. Okay, so the 4x4 means you have 4 antennas in the transmitter and 4 antennas in the receiver. Each of these antenna ports, they use this separate resource grids. Okay, so you have extended capacity. Okay, and the E node B actually assigns the resource block with channel dependent scheduling. Okay, so this channel dependent scheduling is done to exploit the multi-user diversity. So what is meant by multi-user diversity? So let me explain. So let's say you have a scenario like this. So you have two users here shown, and the two users have different types of frequency selective fading. Okay, so the user 1 is facing this fading and user 2 is facing this fading, and let's say if it was a flat fading, then it would have stayed flat like this, but this is a frequency selective fading that both these users are facing. So you can see that user 1 has a peak at these values, let's say, and it has a trough, or it has a dip here in these values, and user 2 has exactly the opposite. So user 2 is high when user 1 is low, and then the frequency response of user 2 goes low when user 1 is high. Okay, so you can allocate the resources, the resource blocks, to these two users in a way that, okay, they doesn't face much fading. Okay, so for example, you can allocate resource block 1, 2 and 3 to user 1, and again 8, 9, 10 and 11 and 12 to user 1, because during these frequencies that these resource blocks have, the user 1 is facing maximum, gain. Okay, and then when user 2 has a maxima, you can allocate these 4, 5, 6 and 7, these resource blocks, to user 2. So the overall signal quality can be improved if user 1 is scheduled at the edge resource block where user 1 signal quality is better, and user 2 in the middle resource blocks where user 2 signal quality is better. Okay, so in this way, frequency selective multi-user scheduling enabled by OFDM transmission can provide additional performance benefit, okay, for LTE system over WCDMA system. So that is what is meant by multi-user diversity. Okay, so the E node B, they assigns this resource block using channel dependent scheduling algorithms so that you can exploit the multi-user diversity which I just explained. So this will increase the bandwidth usage efficiency. This will assign resource blocks for UEs with favorable qualities on certain time slots and subcarriers. And this multi-user diversity can also include fairness considerations, understanding of the UE locations, typical channel conditions versus fading, and QoS priorities. So there can be more fancy things that can be associated with multi-user diversity, but the overall high-level concept is what I just explained. Okay. So in terms of physical transmission, so the release 8 supports up to 4x4 MIMO. For higher releases, you have 8x8. The E node B uses the physical downlink control channel to communicate the resource block allocations and also the timing advances for synchronization. Two types of 1/3 rate convolutional codes are used. So again, you can see how the concepts that some of you have learned in digital communications are getting utilized practically here. So you have learned about convolutional codes in my digital communication class. So here you can see how these things are applied in LTE. Then in terms of modulation formats, QPSK 16 QAM or 64 QAM can be used depending on the channel conditions. So this is a table which gives you an idea about the different code rates and the modulation format that you can use based on the channel condition, and the channel condition is determined by this CQI index. So CQI stands for channel quality indicator. Okay. So CQI indexes actually gives you the condition of the channels, and then based on that you can use simple modulation formats like QPSK or higher order modulation formats like 16 QAM or 64 QAM. And then these are the different code rates. So if you multiply the code rate with 1024, then you get these numbers. Okay, so and then efficiency, these can be calculated based on the code rate. So let's say if your code rate is this, so this means the actual code rate is 78 over 1024. Okay, and then for QPSK, part symbol has 2 bits. Okay, so if you multiply this by 2, then you will get this number, whatever is the efficiency. Similarly, these number, or everything can be calculated based on whether you are using QPSK or 16 QAM or 64 QAM. So for example, for 64 QAM, you will have this 948, let's say, for CQI 15. You have 948 divided by 1024. And then for 64 QM, you are using basically 6 bits per symbol, because 2 to the power 6 is 64. Okay, so this multiplied by 6 will give you 5.5547, which is this number in the efficiency column. Okay, so that's how these are calculated. Okay, so this is the physical transmission part. So now let's see what's the power on procedure. So there are several steps. So first you have to power on the UE, and then select a network, then select a suitable cell, use contention based random access to contact an E-node B, then establish an RRC connection. Then the attach phase comes, where you register the location with the MME, and the network configures, control and default EPS bearers. Then you transmit a packet, and then the mobile can request improved quality of service, and if so, it is given a dedicated bearer. Okay, so so now let's look into some of the concepts of LTE Advanced. So far we were studying 3GPP release 8. Releases 9 to 12 have been also issued. So release 10 meets the ITU 4G guidelines and took on the name LTE Advanced. And here are the key improvements. Okay, so you have carrier aggregation, you have MIMO enhancements to support high dimensional MIMO. In fact, in 5G, which is release 16 and beyond, you have massive MIMO, so where you can have hundreds of antennas in the input and the output. Okay, then you have relay nodes, you have heterogeneous networks involving small cells such as femtocells, picocells, and relays. Then you have cooperative multi-point transmission and enhanced intercell interference coordination. And finally, you have voice over LTE. Okay, so we'll go through some of these concepts, not all. So the first concept is carrier aggregation. So basically the ultimate goal of LTE Advanced is 100 megahertz bandwidth. Okay, so you can combine several carriers. So usually the allowed carriers in LTE were these 1.4, 3, 5, 10, 15 or 20 megahertz. So you can combine these to make combined carriers, or CCs, or sorry, component carriers. You can combine this component carrier. So these are the component carriers to form a combined carrier up to 100 megahertz. So if you combine 5 of this 20 megahertz, then you will have 100 megahertz bandwidth. Okay, so there are 3 approaches to combine the component carriers. First one is intra-band contiguous. So here the carriers must be adjacent to each other. In case of intra-band non-contiguous, the multiple component carriers belonging to the same band are used in a non-contiguous manner. And in case of inter-band contiguous, you can use different bands. So there is a video here for carrier aggregation. I will show you this video. So I will stop for a while and I will play this video, and then I will come back again. Okay.
Carrier aggregation is probably the most important thing that's happening in mobile right now. And the way to think about carrier aggregation is this. If, let's say that this tower serving you is like a beer tap, right? And the glass is a smartphone and the beer being poured into a smartphone is a movie that you're trying to download, okay? If I, fill the glass from the beer tap, then it will take a certain amount of time. But if I were to fill it from 2 beer taps simultaneously, then the beer would, fill the glass in half the time. And that's basically what we're doing. Instead of providing the phone with just one LTE connection, the tower actually connects to the phone using 2 LTE connections or even 3 LTE connections at the same time. Carrier aggregation is kind of the latest way that we have figured out how to really boost the capacity of the network. And once we do that, then the users can experience much higher speeds. So you could be doubling your speed or even tripling your speed. And that's amazing. Let's say I have a big file that's stored in cloud storage, right, that I need to download to my phone. Well, now I can download it in literally a fraction of a time, right? In half the time or a third of a time. Download speeds that are faster, upload speeds that are faster, high resolution videos that can stream without buffering, etc. So solving for capacity is kind of like the quest, the ultimate quest for everything that we do with mobile networks. Honestly, the best way to describe how it works, if you dive deep into it, it's black magic. I mean, it's amazing that we can take 2 connections that exist in physical space completely separately and combine them in the phone in such a way that they can be treated as one much bigger, much faster connection. And that's exactly what carrier aggregation does.
So welcome back after that video. So we were talking about carrier aggregation, and as you can see, there are several carrier like components, and you can stitch them together as the diagram shows to get a combined carrier which gives you better and larger bandwidth. And then you can have intra-band contiguous, so within the same band you have 2 carrier components which you are stitching together. You can have intra-band non-contiguous, so there is a gap between the 2 carriers. But still these component carriers are within the band A. And you can also have interband interband non-contiguous. So the component carriers belong to 2 different bands, and then they are also non-contiguous in nature. Okay. So moving on, another feature of the LTE Advanced is that enhanced MIMO. So instead of 4x4, you can have 8x8 MIMO. You can also have multi-user MIMO, and this can allow up to 4 mobiles to receive signals simultaneously. So the eNode B can switch between single user and multi-user every subframe. The downlink reference signals to measure channels are key to MIMO functionality. Okay, so the UEs recommend MIMO pre-coding, modulation and coding schemes, and the reference signals sent on dynamically assigned subframes and resource blocks. Okay. Then the next concept is relaying. So the relaying nodes are present, so they form extended coverage for an eNode B. Okay, so these relaying nodes they receive, demodulate and decode the data from an UE, and then apply error correction as needed, and then retransmit the signal to the base station. So basically these relay nodes, they function as a new base station with a smaller cell radius. Okay, so the relay nodes can use out of band or in band frequencies. Okay, so here is the concept of relay node. So you have a small relay node here between the UE and the eNode B. So the relay node receives the signal and then relays it to the eNode B. Okay, by doing some error connection and retransmitting. Okay, so this is the concept of relay nodes. Then you can have heterogeneous networks. So it is becoming increasingly difficult to meet data transmission demands in densely populated areas. So the concept of small cells are introduced to provide low power access nodes. Okay, so these small cells, they operate in licensed or unlicensed spectrums, and the range of these small cells are 10 meter to several hundred meters indoors or outdoors. and they are best for low speed or stationary users. And the macro cells, they provide the typical cellular coverage, so their ranges are several kilometers, and these are best for highly mobile users. So the macro cells are basically the existing base stations, let's say, and the small cells are something which is a new technology. So since the small cells and macro cells, they exist together, they form a heterogeneous network. Okay. So you also have femtocells, which are again low power, short range, self contained base stations. So these are even smaller than the small cells, and they actually are present in residential homes, and they can be easily deployed and used in the home's broadband for backhaul, and also in enterprise or metropolitan locations. So with all these small cells, femtocells, macro cells, all of them together, you have many base stations, okay, that are within a small area. So that provides network densification. So basically, let's say if this is an area, and instead of having, let's say 1, 2, 3, 4, 5 macro cells, okay, you can have several, let's say the red color, okay, denotes the macro cells. Now you can have several small cells like this, okay, and then let's say you can also have femtocells. So let's say you have several femtocells like this, okay. So in that way you can see that this area is actually served by so many different cells, okay, and each of them has its own, range. So this is getting dense, okay, this area is getting dense with this network elements, okay. That's what is meant by network densification, okay. So each of them has their own ranges, okay. So let's say this one has a range, and then this one has another range, okay. So these circles denote their range of operation, and with this the entire area is very well covered and well served. So if you have many users in this area, then that users will find a small cell or a femtocell or a macro cell within a very few meters of their existence. So in that way the coverage and connectivity is always good, okay. So that's what's the concept of network densification. And with this densification you have certain issues. So the handovers, so there will be frequent handovers because the user is moving, and the cells, whether it's a macro cell or a small cell or a femtocell, they are so close to each other that there will be frequent handovers. Frequency reuse will be an issue, QoS and security will be issues. So with new technologies you have new issues, and then the researchers solve these issues and new solutions come up, okay. So this network of large and small cells, okay, so these networks of large and small cells together is called a heterogeneous network, or HETNet, okay. So this diagram shows the role of femtocells. So you can deploy these femtocells in your building, okay, as a access point, okay, as a local access point, and you have several devices that actually connect to this femtocell, and through this router it is getting connected to the rest of the internet, and then to the mobile operator network, and then to the cellular tower, and then this tower is actually serving some other mobile phones or some other devices. So from here to here you can have coverage through this femtocell, and then through this cellular tower. So that's the role of femtocells. Then the next concept is called coordinated multipoint transmission and reception. So release 8 provides intercell interference coordination, and also release 11 implemented this coordinated multipoint transmission and reception. So I will so this is a bit of a complex concept, so I will not go through the details of this, but if you are interested, let's say, then you can go to this link here. Okay, sorry, you can go to this link, okay, to learn more about coordinated multipoint. Okay, so this will give you a lot of insights about coordinated multipoint. Okay, so I am not going through the details of this because this might overwhelm you a little bit, so I will better just go through this concept. So in coordinated multipoint you have these several steps. So basically the introduction of MIMO actually has facilitated this coordinated multipoint. So you have different antennas, and you can use those antennas for coordinated scheduling and beam forming, and then you can have joint processing and dynamic point selection to have overall signal quality and quality of service which is much better than, let's say, a single antenna scenario. Okay, and then there are several other enhancements in LTE Advanced. So you can have traffic offload techniques to divert traffic onto non-LTE networks, for example from your LTE network to the wireless LAN if you are inside a building with a wireless LAN functionality. Then adjustable capacity and interference coordination, enhancements for machine type communications, and then support for dynamic adaptation of TDD configurations so that traffic fluctuations can be accommodated, and many more. Okay. In release 12 there are also some studies to enhance to higher modulation formats, okay, like 256 QAM, okay, and also two-dimensional arrays that could create beams on a horizontal plane and also at different elevations for user specific elevation beam forming into tall buildings. Okay, so these are some other enhancements in release 12. Okay, and then finally we have voice over LTE. So basically the GSM association it documents the additional specifications for issues that 3GPP specifications cannot implement. So within this GSM association they have defined profiles and services for voice over LTE, and they uses IP multimedia subsystems or IMS to control this delivery of voice over IP streams. And IMS is not a part of LTE, but it's a separate network, and it's mainly concerned with signaling. Okay, so the GSM association is taking care of this IMS, and it also specifies services beyond voice such as video calls, instant messaging, chat and file transfer in what is known as the rich communication services. So again, I'm not going to the details of this, but I'm trying to give you a overall concept. So if you want, you can do some self study to know more about these topics. Okay, so with that I will end this lecture, and I will share some additional reference materials to you on LTE which you can study to discover more about LTE. Okay, so thank you for now.